So I'm very, very honored to be invited and give you my point of view on model order reduction and where it can help us. I split the talk twofold. On the one hand side, looking at that, what can it do for industry, industrial applications, and then in the second part, looking on the methods, but also the very specific twist, looking on the methods from an industrial background. Well, the talk is about digital twins. We do hear these days a lot about digital twins, and to make it even more complicated, it is about executable digital twins. I'll explain a little bit more in detail what this is about. I think the key thing is that model order reduction and scientific machine learning, both together, are really two key technologies or key building blocks of this endeavor. Of course, there's always a huge crowd of people to thank, and I hope I didn't forget any one of my collaborators through this journey. Maybe a question and to explain a little bit what has this to do with Siemens in general. Many of you might know Siemens from washing machines, from gas turbines, from computer tomographs. But that is really more something of our past, and at the core of Siemens AG today, the core ambition is, as our boss, Roland Bosch, the CEO, says, to combine the real and digital world like no other company. So that means we have, in a way, spun off several of these companies, and our core businesses is now really focusing around that, combining the real and the digital world. How do we do that? Well, those of you following Siemens for a longer time do know that we have a large footprint in automation systems, so automation on the factory side, manufacturing, or in the building side. So many of the buildings and plants run on Siemens control. And in the last, 15 to 10 years, there has been a major transformation also on our business side, building up a huge software business. So Siemens has invested $10 billion over the time, and is now really one of the largest software providers when it comes to R&D software. So all the way from computer-aided design, computer-aided engineering, computer-aided manufacturing, plus additional software supporting the operational part. So that means these days we not only have a big footprint in the production and performance of buildings and manufacturing sites, but also in the digital tool chain to design those things. And bringing this together is really, or allows us to combine those two worlds, and that's how the digital twin has been coined. But what is the digital twin? Why is everybody talking about that, and why am I putting here that really on the center stage, speaking about model order reduction and scientific machine learning? So first of all, it's really not new. In the end, it is a very, very old story, yes, going back to NASA a couple of decades ago, where people really used physics-based simulation and modeling capabilities, trying to understand the systems first only for troubleshooting. And then they figured out, well, that is a quite useful technology to understand things first in virtual, so that it really became a major workhorse in all R&D departments. And probably today, no product is designed without being designed first in virtual and then also validated in the virtual world. So what is new about digital twin? And what is really new is that I would go here. Oh no, well, first let's get a step back. Why do we speak now about digital twin? What has really changed here fundamentally that we do that? And I think really what has changed on the one hand side is on the enabling side, so computational power, the capability of our algorithms, the capability, the semantics, the standards to integrate models on the different system levels, as well as the capability to collect lots of data. So lots of things on the enabling side have changed, but also on the driver side. Yes, our products and our systems get much too complex to be understood just by looking at them. Yes, so we really need novel ways, not only to design them, but also to control and operate them. Otherwise, we'll not manage these systems. And I think we absolutely need to do that if we would like to manage the big challenges ahead of us, like becoming CO2 neutral. So I think that there's really has happened quite a lot on the enabler side, and there's also many drivers pushing us. So what is then new about the digital twin compared to what we've done before? And I think really for me, the key thing is really stepping from this model-based engineering, so using all those models only during the engineering, maybe commissioning phase, doing that step along the complete life cycle. So really using these technologies during operations, and that will be a major focus of this talk. So try to explain what it is not. So it's not really something like a digital doppelganger, how those of you who have seen the movie The Matrix, how it is depicted in that movie, but it is really more, from our point of view, a comprehensive set of digital models, which is accepted as a full substitute for reality, take decisions for specific purposes. And that could be super realistic models, depending on the use case, but it could be also only a very rough model, order of magnitude, giving you a qualitative feedback, showing you what to do. Yes? And all these different models together, that really makes up the digital twin then in the end. There's a very nice movie linked here, so please feel free to go to that link and watch that movie. Last but least, the story also does not end here. Yes, these days, not only Siemens, but many of the industrial companies together with NVIDIA start to talk about the industrial metaverse. So this is really then about democratizing these things more even further, putting real-time requirements, capabilities further, exchanging models like you would exchange the real goods. So I think lots of things you can imagine around that. But let's stay with a digital twin for the moment, not even try to go to the bigger thing while we have not yet really solved the digital twin challenges. So digital twins, why is there a need to introduce something new like an executable digital twin? Why do we need yet another concept while it seems like we not really manage the digital twin at all? And as I said, for me, the key point is that with the digital twin, we'd like to go to the operations phase of things. And this is a survey, roughly 400 people answered to this survey. So what are the major pain points for a broader adoption of digital twins, really, when it comes to the operations, so the post engineering phase? And well, probably not surprisingly for us, yes, calculation power is abundantly available, so that is not an issue. But it's really, we don't have enough real-time models. Building the real-time models whenever required is quite a pain and quite a lot of manual labor. It's a super complex software landscape. Yes, all the different engineering simulation tools, the IT, the operational technology, etc. So in the end, you can only run that by having lots and lots of experts, and we simply do not have an amount of the experts required to do that. So in short, you could say, okay, digital twin today are really kind of slow and bespoke when it really comes to putting them into place, specifically for the operations. And that is really where we came up with this concept of an executable digital twin. So what is it? It basically is two ingredients here. The first idea is today in the R&D phase specifically, typically the model and the software is decoupled. Yes. So first of all, you need to buy a super expensive software, install that software, and then you can import a model or model within that software. So it's really decoupled. And the key idea, one of the key ideas, is to have really a self-contained, executable digital twin of that specific asset, which has all the not only all the model, but all the prediction capabilities, and also the solver included. The idea is then once we have such a thing, well, then it can be leveraged basically by anyone at any point in the life cycle. Probably from mathematical point of view, not really fancy. Still, we put that forward in a conference proceeding a couple of years ago, and actually, I'm personally quite proud of this conference proceedings, because that is probably the only mathematical, well, not really true mathematical in terms of theorems, et cetera, and lots of calculus, but a paper in a mathematical journal or conference proceeding, which made it into an industry analyst paper. So just to show and underline a little bit here how much getting these things self-contained real time, so it can run really, and real time it means a lot of different things, as we'll see during operation, is something which gets industry or the industry community very excited. And here, of course, model order reduction and scientific machine learning are two of the key technologies to do so. But let's talk about an example. So it's a rather old example, already 3-4 years old, but still, I think one of the best examples we have realized, at least in our labs, showing really the limit of what is possible. So the key challenge here is, can we teach a robot or get a robot enriched with a piece of software so that it can perform metal milling? You might say, okay, I've seen lots of robots doing milling of wood, plastics, foams. That's quite easy, but metal milling is something impossible, and at least up to date. And the main reason is you have quite high forces when you do that milling, 400 Newton around, sometimes more, sometimes less, and 400 Newton, that is enough to push really the robot for 1 millimeter or 2 millimeters away. So that means the tool center point is moving 1 or 2 millimeter away from the intended path. And that leads to an inaccuracy, which is really not acceptable in any kind of manufacturing process. And so the key idea here, what we did is, on the one hand side, we set up quite a complicated model, combining some heuristics, machine learning for understanding the expected forces during the process of machining. And that can be done basically by relating the amount of material where it is removed the material to the expected force. And then once you know that, you can feed that information to the robot. And on the robot, there is real-time multi-body simulation anticipating what is happening due to this force, and which then can correct. At the same time, we close the loop. So you also have a few sensors on the robot. The most important sensor is probably the torque sensor of the tool. And you can use that information to also calibrate the model and force prediction, because typically, I mean, calculate that somewhat accurate during the manufacturing preparation, but then the operator overrides some of the settings because he knows, a very specific machine would perform better or whatever, and that's why calibration part is here an important ingredient, to have that in a loop and to increase the accuracy, even for situations which have not been foreseen during the planning process. This is the or one of the pieces showing here the results. And again, there's a link in the bottom right. You can look at a much longer video explaining what's really going on there. But the key thing is shown actually here. So this is the deflections without any correction. And here it's plus minus 1 millimeter. As said, that's quite too far for any industrial machining tasks. And then this is with the correction switched on, you actually go down to 0.1, 0.2 millimeters in accuracy. Well, still for the finishing, it's not enough, but for the roughening part of the machining job where you remove most of the material, that's far enough. And this really allows having this digital twin on top, running in parallel with the robot, actually on the standard robot control, allows to enrich the accuracy. And that's not only fascinating to see here really what advanced control strategies combined with the prediction can do, but obviously also you can use that now on machine tools to increase the accuracies. Yes, and a machine tool, the price, the material used for a machine tool, that typically scales or is proportional to the accuracy, because accuracy you buy through making the machine very stiff. But the nice thing is now you can increase also the accuracy by just adding a piece of software without adding additional hardware. And that means, well, you can spend less buying new machine tools, you can retrofit maybe things, and in the end, also very much supporting sustainability. And of course, you can do many more things. So this is a demonstrator we did, and I think very often show together with AWS on fairs. Enriching here on top an augmented reality visualization. It's a different robot here, which you then can use to do troubleshooting, understanding what is going on. In this case here, why do stresses in certain situations occur? And is that due to an issue on the robot, or is that due to an issue of the setup? So you then can do troubleshooting just as one example. So I think the fascinating piece here is that, yeah, just using a digital twin, you can enable what people thought, okay, this is kind of impossible. Yes, if we would have spoken a couple of years with someone on the shop floor asking him, can you do a metal machining with a robot, that will be a clear no. And that helped us a lot to circumvent a little bit in the beginning. Is that really scalable? How much business can you generate with this? So I think it was really about demonstrating something everybody believed to be impossible. We spoke about we can decrease the manufacturing error here by 90%. And the nice thing is this does not really require any additional experts on the CAM side or on the operator side. So it's rather quite easy. Of course, you need to install a different piece of software during the CAM as well on the robot. But in general, it does not really change the workflows, doesn't make anything more complex. So this is what I personally, one of my favorite examples, how to use digital twin in a real-time context. And maybe because we spoke also about real-time. So real-time means here a prediction every few milliseconds, because I think it's something between 1 and 10 milliseconds, or something between every 1 to 10 milliseconds, a new decision how to move is taken on the robot. And of course, we need to anticipate how this would be deflected so that we can correct that. So real time means here really a prediction every few milliseconds. Whereas then, of course, if we speak about terminal effects, then real time means something completely different. Yes, real time would be maybe a minute to 5 minutes. That will be far enough to do predictions. So that's why I like this here particularly, because really going to the extreme, and you also only manage that if you do really have the model running on the control and there is no chance to do a lot of things on the edge, specifically when you do have long communication times. That is the application side. I'd like now to spend a few minutes to speak about the mathematics behind it. Probably not as sophisticated as we've seen in the previous talks, but rather trying to put a focus on here what is important from an industrial point of view, or what kind of algorithms really have proven to work in an industrial environment. Well, first of all, the one approach is knowledge-based simulation models. So that is really where I'm coming from. Yes, from part of Siemens, where we do produce simulation tools. Physics-based, so very much driven forward by knowledge. And then, well, we all know machine learning, the volume of relevant data have significantly increased. And I think really also if you speak about digital twins or executable digital twins, model order direction, then these days it's really about trying to marry those two paradigms. So a very big focus when we speak here about scientific machine learning or machine learning in general is really all about accelerating prediction capabilities of tools to have faster decisions. And well, that is on the one hand side, we do employ quite a lot of machine learning or research, quite a lot of research on the simulation solver side. How can we use machine learning to really accelerate the solver? And that is done basically by marrying really quite closely classical numerical algorithms combined with neural networks. And then on the other hand, the surrogate modeling, where we just take data combined maybe with physics knowledge to have really these real-time capable models running in parallel to the operations. And then you have plenty of different use cases all across Siemens. So I don't really speak a lot about the solver acceleration here. If you're keen to curious to learn more, just let me know. Happy to share more details afterwards with you. So really tried lots of different things, starting from optimal grid refinement all the way down to accelerating really the linear algebra by means of machine learning or neural networks. And actually on the right-hand side, the linear algebra acceleration or acceleration really on a similar level is our focus these days, because very nicely, if you do things like here, so here we basically replaced the very fine scales of a geometric multigrid solver by means of machine learning. And that, of course, well, the smoothing process, the prolongation restriction in that setting is a local phenomena. Yeah? So if you do something like this, linear algebra or learning turbulence models, and then machine learning would only learn on local structures, and that allows you a much richer data set, because all of a sudden a simulation is not a single data set, but really hundreds of thousands of data sets. Whereas when we looked at this optimal grid refinement, really in that setting, each simulation was, or each optimal grid was one simulation data set. And that was quite a lot of data, which we required to come to some satisfying solutions. That only to show a little bit what we are also doing in our group. So this is also an forward a focus, but I'd like to speak today a little bit more about the surrogate modeling. I think we've seen a lot, what I would call here good model order reduction approaches. Yes, if we do have access to all the system matrices, etc., then we have this enormous set of very, very nice model order reduction technologies. A big challenge for us is actually to have access to these matrices. And that is not only due to the fact that we're working with commercial solvers, yes, where a commercial solver might, for a certain reason, decide not to open up inner structures of matrices or whatever. But if main reason here is actually, if you look at CFD cases, yes, then most of the state-of-the-art CFD solvers, they are all matrix-free to be nicely scalable, HPC capable, etc. So it's really, really hard and would require an enormous effort to somehow get access to the right matrices, build them up, or run classical algorithms on them. So that's why we actually prefer to go with, well, what probably many engineers as well as the mathematicians would call the BAT. So we are very much looking at regression-based model order reduction, so inspired by machine learning, and trying to look at what we could do data-based. And we'll have an example of that afterwards. And last but not least, the ugly, I think, working on industrial problems, getting the right and good sampling strategies, how to get your data in such an industrial workflow is very, very crucial, but very often forgotten. And I think really if we try to look about what is missing on the industrial side, I think really getting things automated, such like sampling, if we like to do data-based model order reduction based on samples from simulations. But let's start with a regression-based model order reduction. Two typical use cases would be here. On the one hand side, we do have a very complex process planned, lots of reactions, and you have reactors, for example, multitubular reactors, where the reaction takes place in tubes, and outside it's cooled by flow. How can we predict the thermal behavior? Well, that would be actually nice to have a complete CFD model of what's happening on the cooling side, a very specific design of the reactor and how that reacts then with the actual reactions, which are modeled on a systems approach. And in order to do that, well, we need a reduced order model, which we then can plug into such a system simulation tool. Other use case, also probably quite prominent these days, electric batteries. Thermal runaway is a big issue. So how can we control the thermal behavior of a battery? Works quite nicely with classical Moore approaches if you just look at the thermal part. But at the moment when you add the cooling, if you would like to add chemistry, well, then you have all this issue with not having access to matrices. And then again, how can you reduce these very complex 3D simulations into a system model, which you maybe can put into control, or simply you use it in a system simulation to drive a complete drive cycle. I think in this seminar, we have heard a lot how all this works. Yes, you start from snapshots. You identify a lower dimension, a latent dimension. Could be autoencoders, diffusion maps, dynamic mode decomposition, or POD, proper orthogonal decomposition. Then in that latent dimension, that reduced space, you try to identify the dynamics. And once you do have that, you then can go towards a reduced model. Our favorite setting here is actually proper orthogonal decomposition, mostly because this works quite nicely together with operator inference. Yes, the linear combination of the modes allows us to also understand immediately what would be the nonlinearities of the model. Yes, if you would do from standard finite elements, but also you don't change really the nonlinearities of the models using a linear set of ansatz functions. That really combined the proper orthogonal decomposition with operator inference, we feel is working quite nicely. However, the issue here for the operator inference, but very often also if you work with neural networks, is that many of these state-of-the-art approaches require good estimates of time derivatives. And getting those good estimates of time derivatives is quite tricky, because very often you do have large time sets, because you're limited in the disk space you have, as an example, to write your data. So getting this is very difficult. And then also you always have in these least squares optimization problems, this regularizer, well, you also always need a magic number. How does that influence the quality of your prediction? And that is very many magic constants. So we spent quite some time thinking about how can we do this better. Well, actually, the key idea is we move from a least squares optimization problem or unconstrained optimization problem to a constrained optimization problem. So we are not minimizing what is the dynamics we observe, so the time derivative, and what will be the corresponding right-hand side. But we really rather ask, what would be the corresponding model, simulating a set of a trajectory, and choosing the model parameters such that we really fit or correspond to the observed trajectories. The very nice thing taking such approach also is that we do not need necessarily to observe all our variables. Yeah, so it's enough if we have a subset of the actual low dimensional approximation and observe that. Or add some additional data we can observe from a real experiment. So we have a much bigger freedom in terms of choosing what we like to optimize. So this has many different names. It has been introduced as neuro ordinary differential equations, solver in the loop, unrolling. I very often prefer to actually state that this is nothing else than what we know from constrained optimization problems, whether it's parameter optimization or model predictive control from dynamical systems. So what you in the end do is you take your forward problem, you calculate the KKT conditions, which requires you to solve the backward problem, and then you can optimize the whole thing. And what you can see here, it really nice, it works out nicely. This case for this complex cooling flow on the left-hand side is just a standard operator inference where we just infer basically the dynamics from one time step. And on the right-hand side is that when we do that along longer trajectories. What you do still here see is the spike in the middle, but the spike is actually from an insufficient approximation from the POD basis, because there's basically a switch in the dynamics. And the nice thing, if you do so, well, you reduce your order error. It's super robust. You don't need to invest any time finding magic constant anymore. You do not need to spend any time figuring out, is this now good time derivatives or bad time derivatives? And it's extremely robust and allows you really coming from a physics model with 400,000 degrees of freedom, a CFD model, all the way down to an ODE with 8 degrees of freedom with explicit matrices. And actually you see here an exponent in there. So we put in a little bit more knowledge and actually combine the operator inference here with a DIME approach. So this is very much, or hopefully very much, reflect what is important for us. It's really about accelerating the prediction of that and not losing accuracy. So that is the need kind of using this approach. Well, we get explicit equations, which we then can reuse in many tools and systems. Yeah? And having an explicit set of equations is very often easier than neural network. For example, if you would like to implement it directly in a controller and really bring in this differential solver technology, however you call it, solver in the loop, optimal control, parameter estimation, that make really things a lot easier, and it has been revived a little bit in this setting in the machine learning community, but it also works here for the operator inference quite nicely. Well, issue is still the data generation, and of course also the question, how can we guarantee a little bit the errors? last but not least, as I said, the biggest pain for many applications is probably how to get the right sampling of the data. So in general, you would have a tool. In our case, that tool is called ROM Builder, which then samples a CAE tool, doing high fidelity simulations, generating a huge set of snapshots, and then out of this, building the reduced order model you're going to then reuse in whatever application. And then, of course, there's tons of additional management you would need to do. Make sure once you change something on your model, on your hardware, you need to make sure that on the control, the model needs to be changed. So a very, very big also product lifecycle management issue, but we're not speaking about that here. So rather about how can we do this sampling efficiently. And just an explanation why this is not as trivial as one originally might thought. Yes. This is two sampling strategies actually we started for. We call it static sampling and dynamic sampling. Static sampling means, well, we take a set of parameters, keep that set of parameters fixed, and then run the simulation for a long time for this selected set of parameters. Or we do a dynamic sampling where we change the parameters randomly all over time and can much nicer, as indicated here, cover the whole space of parameters. Now, the initial natural reaction would be probably, yeah, the dynamic sampling is much better, but that actually is wrong. Because if you do have only few samples and keep them fixed, you of course really have a chance to explore the system boundaries and go to the extreme cases. And so if you change your parameters every few seconds and keep that very dynamic, you're very likely sampling only around the mean, and you do not learn much about the system. Then, of course, the question or other questions being put forward here are very much by Benjamin Piersdorfer. Would you do a long trajectory and then project, or do you do small trajectories, then project back, do further simulation? So many questions how to do that effectively. I would like to focus here on the approach we proposed some time ago. So the key idea is we start from a full order model, generate a set of snapshots. Out of these snapshots, then generate a reduced order model, so POD in this example, and combine in a way what we call joint space, the POD together with the parameter space. And that is the space, so the different coordinates of the POD modes and the various parameters we would like to sample. Then we generate a data pool and a validation pool. We introduce here a measure which we call probably approximately correct, which associates a probability of having a certain accuracy in the prediction. That is really the key measure for us when we decide whether we do have a good sampling or we need to resample. And then the active learning or the active sampling goes exactly the same way. Yes, we do have a data pool. We have a set of samples in this joint space. We have the full order model to generate training data. Out of this, we generate the reduced order model. We do check, are we approximately correct? If not, we are going to resample. And the key thing here is we estimate really, this case by means of a Gaussian process, the error of the ROM snapshots, and then do additional sampling in spaces in this combined parameter coordinate space where the error is rather high, and we iterate that as long as we're happy with the accuracy, and then can export the ROM. And this really makes life a lot easier for industrial users of these things. And let me jump a little bit over this. So I think let's focus here on the bottom left, where we see that basically with 20,000 samples for a neural network, if we do the active learning, we go down to an error of 1% compared if we would just use random sampling, we would have an error of 13%, and the same holds for the operator inference. We can really increase the accuracy, and also what you see nicely here, because the number of nonlinearities in the operator inference are much more restricted than the general very nonlinear neural networks. In general, we get better results with a smaller number of samples. And these error we give here, so an error of 1% means, well, we are 97% confident that we are really below this. I'm not talking here too much how we do the error estimation. I would just refer to the paper afterwards. So let me wrap up here. So I think really key thing for us is to increase the automation for the industrial workflows. We do believe that having such an active learning strategy helps a lot to come really towards optimal reduced order models. And well, this is the first heuristic strategy, but it's really worth to look even further into this. How would you sample? How can you come up with good error guarantees, etc.? Because I think really this analytical guarantees is still a big challenge for many methods. With this, let me wrap up. I basically took you a little bit through the story from the digital twins. Well, hoping making the case that this is not new, but what is really new, going to the operation phase where we'd like to use those models for the operation. Again, you might argue nothing new. Model predictive control is of course there for ages. Virtual sensors is there for ages. But this is really about making that more streamlined, reducing the effort of engineers, operators to set up these simulations. I think there's still a lot to do to really realize these for industrial cases, and we are far beyond from a big scalable approach up to the extent we would really need it to manage the challenges ahead of us. But yet, well, probably industrial companies as well as academia always come up with new concepts, and with the industrial metaverse and ideas around that, I think the challenges are even higher. So I think it's really a great time to start in this field, to look for challenges, to develop new research. And with this, I would like to close. And if there is any, well, first of all, let's have a couple of questions now, but also please feel free to reach out afterwards if you do have questions. So thanks once more for inviting and having me.
Thank you very much for the nice, wonderful talk. It was great to see the industrial usage and the challenges around that point. So I have a few questions for you. So, for example, you mentioned that error in digital twin is, let's say, a bit of problem. So, for example, how does this vary across different applications? For example, in machining, etc., you need the accuracy of the order of 1 millimeter or maybe even less in critical manufacturing. But if you are estimating stress, you will have some factor of safety. So how does this error requirements vary across different applications? Yeah.
I think it varies very much, yes, and that's why this machining of the robot is also a nice case. Yes, if something goes wrong, well, probably in most cases the workpiece is damaged. The machine tool itself is damaged, but the robot isn't harmed. Yes, and then even if the robot isn't harmed, okay, it's just a robot. But if you would put things, and we also looked at that, for example, thermal control of motors or stresses of motors in the process industry, then it's very much about, can you increase availability, because uptime of a plant is immediately turns or can be calculated in money. Yes, so uptime, additional uptime of an hour for a process plant, that's already a couple of €100,000. But then, of course, if you do that, you really come closer to those safety margins. And if you cannot, on these safety margins, give good error estimates or guarantees, then that will be very hard to adopt and take these things really into practice, because it's far, or the risk is far too high in terms of budget at risk, but of course, then speaking process industry, also maybe environmental things, etc.
Okay. Yeah.
So
And that is
it's a
also,
big thing, and yeah, that's why it's really, I think, very rewarding subject also to look further into it.
yeah, and that is also related to some of my second question, that because you mentioned about POD, and I'm not sure. So have you done any case study of using autoencoder or something, a plain application, or is the lack of error estimates is actually actually an obstacle for deep learning or machine learning based approaches? Yeah.
Um, so I think for many of the operational cases, um, I think POD works quite nicely, um, because you do have the chance to quite well sample this parameter space, etc. Also, very often that's used in the context of thermal problems, which is not very nonlinear. But of course, where we do see limitations when it comes to POD is when we look, let's take as an example, external aerodynamics, where probably most of the use cases will be more in the design phase, accelerating that, but then flow separation comes in, etc. Yes, turbulence, and then POD is a very hard thing to do, specifically if you put in kind of general or even unknown geometries. So we do look also in how could you use autoencoders. There's been quite a few theses with students working on diffusion maps. But really from industrial point of view, it's really those POD, they work quite nicely. Yeah? And the main reason is also well, not only in terms of computational time, but you can also see immediately the error decay, how much modes would you need. Yes, you calculate maybe a few more, and then just on how it decays, you cut it off. In the end, you only get a single matrix. Yeah? So and the single projection matrix you can then put explicitly on the runtime to then, well, you probably even not need the whole matrices, but just a few temperatures at the points you're interested in. Yeah? So it's only a couple of lines. And that's, of course, all much more handy than working with the neural network. But also, there's a couple of use cases. External aerodynamics is one example where POD sees its limitation. And where also more research is required. And then also maybe, I mean, it sounds like how I presented, maybe that's a good disclaimer, a little bit like jack of all trades, model order reduction tool. Yes, I don't believe it is like something like this is there. So whatever you would do, it's better to have a toolbox of different options.
Thank you. Yeah, for sure. Thank you very much again for a very interesting talk. And if you have questions, please refer to Dr. Hartmann's work, or yeah, as he said, you can contact him.